this part B, the problem is efficient polynomial evaluation. And here we use several small topics to, find a solution for this problem. Yeah. B.1, evaluate the polynomials. First, let's understand the environment around this problem. Yeah. All right, our problem 1. So in this class, we will solve a sequence of computing problems. This is the first one in our sequence. Yeah. All right, the problem description, given a polynomial. The representation, standard representation like this. Yeah. All right, yeah. Here you do not know how many terms. Yeah. So here we use this ... Yeah, could be any number of terms. Yeah. And we will solve this general problem for any number of terms. Sometimes the number of terms could be very large. Yeah. Thinking about 1,000, 10,000, 100,000, even 1 million. That many number of terms could be possible. Yeah. With coefficients. Yeah. The coefficients are given in an array. Yeah. All right. Yeah. As an input array. Yeah. After the coefficients given, we fix it. Okay. Yeah. Next, then we take a variable x as some value. Yeah. Every time we can change our variable x value. Yeah. All right. Yeah. Under the same coefficients, then we evaluate this polynomial. All right. Now the question, how to evaluate P of x efficiently? Here, the most important thing, we want to find an efficient solution. Yeah. What do you mean efficiently? So here, it should be very fast, right? As fast as possible. Yeah. So you can see, we really care about the response time, fast response time to make our customers happy. Right? Yeah, that issue. All right. Yeah, here I'll give you the reference in our textbook. Yeah, here you can see I jumped to section 6.5 immediately. Yeah, so in our first problem, I jumped to, a very late section, chapter 6, section 5. Now, the page number I also give to you so you can, read the text there. Yeah. Here, let me give you the reason why I do not follow the natural order. Now, some students ask me, so why you do not follow the natural order? So here, let me give you the explanation. There are several reasons. Yeah, I like to pick this problem as our first one. The first one is easy to understand. Yeah, we know polynomials well, right? Yeah. So we have the background knowledge for this topic. Yeah, the first reason. Second, the solution is very smart. Smart, all right, yeah. Yeah. So I like to use the smart solution to impress you. Impress you, okay? To show the power of algorithm. The reason I want to impress you, to show the power of good algorithms, okay? Bad algorithm has no power, all right? The good algorithms are very powerful, all right? Yeah, so that's what I mean. And another reason, also very important, prepare for our programming project number 1. I will use this topic as our first programming project. Yeah. Let's recall the timeline of the schedule. Now, in our first lecture, I talked about syllabus, and I show you the timeline of the whole semester. Yeah. At week 3, third week of the semester, I need to assign you programming project number 1. Here, so I have to cover the materials first. Yeah. This is the one. Yeah. After we have a lot of discussion on the smart solution of this problem, so then we can do some interesting project. All right, so that's the reason. Yeah. Now, let us find the solution step by step. Yeah. All right. First try. Yeah. At the beginning, we may not get the best solution, right? Yeah. So we have to do a lot of work to find the best solution. So our first try, yeah, we just want to find a solution first. Yeah. We don't worry about so if the solution is fast or slow. Yeah. At this point, just one solution, okay, to get us started first. Yeah. All right. We just use the straightforward algorithm. Okay, yeah. Everybody knows how to evaluate a polynomial. Right? Every one of you knows how to evaluate a polynomial. Yeah. Because you just do additions and multiplications. Okay, yeah. In your, probably primary school, you already know how to calculate a formula with additions and multiplications in certain order, right? The order is important, but you are familiar with that kind of calculation, okay? And it's also easy. You can write a computer program to do that calculation. Yeah, that's our straightforward solution. All right. Yeah. So when we start, let us look at that solution first. Okay. Yeah. To do that, we need to work on each term, right? So this is a representation of each term. Yeah. In this term, we only need to do multiplications. Yeah. If we can find the values of all the terms, then we just do additions to get the final result. That is, the straightforward method is that easy, right? Yeah, yeah. But here, we need to count the number of multiplications. Yes. For this typical term, right? How many multiplications do we need? Right? That's a counting problem. Our first small subproblem, it is a counting problem. Okay, yeah. So here, counting in discrete math 3000, So the, prerequisite for this class, the background knowledge you need to have, how to do the counting. Yeah. Can you recall? Yeah. Some counting technique you can use. How do you find the number of multiplications in order to calculate this typical term? Okay, yeah. If you know the answer, you can type it in the chat area. Yeah. Later, I will give you the answer. Yeah. Later, we need to find this answer. Yeah. But here, we can delay a little bit, right? Yeah. So it's not hard. Yeah. All right. So we need to find the answer. Okay. Yeah. If you know it, type it in the chat area. Yeah. All right. Next. Yeah. Question: is your algorithm efficient? No. So we know how to solve this problem in the straightforward way. And here, the typical way we do in this class, we're not satisfied. If we find a solution, we're not satisfied immediately. We need to consider another question after it. The question is it possible to make our solution better? Is there any room to improve the efficiency of our solution? Here, we need to consider this question. Okay, all right. Find the performance number of this algorithm. Yeah, because here, how do you describe if an algorithm is efficient or not? Right? Yeah, it's pretty vague, right? If efficient or not, efficiency. Yeah. So here, that means we need some measure for performance or efficiency. Yeah. So in this class, performance and efficiency, the same thing. Okay. Sometimes we use performance. Sometimes we use efficiency. Okay. Yeah. Some special measure. We need to find a good measure. Yeah. All right. Are we satisfied with this solution? At this point, we cannot answer this question because we only have this solution. We do not know any other solution yet, right? Yeah. Only when we have more than one solutions, we can do comparisons, right? Here, we only have one solution. How do we know it is good or bad? Yeah. We have no idea. Okay? Yeah. So in order to do some comparison, we need to do it, we try to explore more. Yeah. All right. Here, Thomas, count the number using the multiplication rule of, do not use probability, just number 1, 2, 3. 1, 2, 3.
Oh, whoops.
Give me a number. Yeah, because probability, that's a number between 0 and 1, right? Yeah. So we do not use probability. Yeah. Just concrete integer. Yeah. Positive integer. Yeah.
Oh.
All right. Yeah. Another try. We still have time in our second topic, we will get there. All right. Yeah. So we still have a few minutes to get that answer. Yeah. All right. Next. Analysis. Do we really need an algorithm here? Because this problem looks so simple. Everyone can find the solution easily. Why we need a fancy algorithm, right? Yeah. The answer is simple. If we can improve its performance or efficiency, we should do it, right? If we can make it faster, we should do it. All right? Yeah. That's the reason. Yeah. Yeah. So let's see. Can we make it faster? Much faster, right? Yeah. It only contains addition and multiplication operations. So the things we need to do so simple. Additions and multiplications, so simple. Yeah. How can we make it much faster? Right? Yeah. Here, let me give you some hint here. Let me give you some hint here. All right. Although we only need to do additions and multiplications, but when we do these additions and multiplications, which order should we follow? There is certain order, right? Multiplications first, then addition, do additions and multiplications in what order? Think about that. Order is important. Evaluation order. Operation evaluation order is important. Okay? Yes. Because you have freedom to evaluate in different orders, right? Yeah. That freedom, we can take advantage of that freedom to get a better solution. Yeah. Here, it's hard to see it. So we will, do a lot of things before we can get there. Yeah. All right, next. Yeah. Can we use the execution time for efficiency measure? Yeah, because when we try to look at the efficiency, we need some number, some measure to tell us good or not. Yeah. The first measure we can think of, execution time. Yeah. Here, yeah, the answer is execution time. This one not good. This measure is not good. Yeah. Why? Why not good? Because not stable. This measure is not stable. What do you mean not stable? Because different people, they use different computers, right? Some people, they may have a lot of computing power, okay? Like Google company, Facebook, those giants, they have a lot of computing resource, okay? So they can reduce the execution time, big time, right? But for ordinary person, we do not have that much computing power. We just use our PC, yeah. So definitely we cannot, it's not fair to use that execution time to do comparison, right? Yeah. So here I say not stable, yeah, because for different computer resources, the answer will be different. Yeah. We like to find a stable measure. Yeah. No matter you use super computing resource or just ordinary simple computing resource, the measure should be the same. Very stable. Okay, yeah. All right. Then a good choice is using the number of additions and multiplications. That is stable, right? When you use supercomputer, you know, lot of computing resource, when you count the number of additions and multiplication, the same number as you implement on the ordinary PC. Okay, yeah, so it's a stable measure. Yeah. All right, but for this measure, here, because we have additions and multiplications, so here there are two different operations, right? Two different operations. But when we count the number of additions and number and multiplications, how do we use one number as the efficiency measure? One number, right? Because addition and multiplication, each operation, they use a different amount of time, right? We know addition is faster than a multiplication in a computer. Okay, so here something like you compare apple and pear, right? So it's two different things, two different objects. How can you compare two different objects? Addition and multiplication. So here we just need to do some assumptions. We need to add some reasonable assumptions in order to compare addition and multiplications. Yeah. So that assumption, let's assume we know addition is faster. So the amount of time used for each addition is 1 unit of time. Okay. Yeah. Abstract unit of time. Okay. Yeah. Just 1 unit. Yeah. Each multiplication takes 10 units of time, 10 times of one addition. Yeah. Yeah. So this number, yeah, here you may ask me why you make this assumption, 10-to-1 ratio. Why you make this assumption? Yeah. First, we know the assumption is simple, right? Yeah. So it's a, approximate number. It's an approximate number, and it's close to the real world case. Yeah. In the real world, pretty close to this 10-to-1 ratio. Okay. Yeah. All right. Okay. So it's a reasonable assumption. Yeah. Next, now we need to, try to move forward under this reasonable assumption. Let us use one number to measure efficiency. Okay, yeah. Find the number of time units, just one number. One number represents the number of time units we need to solve this problem. Okay, yeah. All right. Here, yeah, you may like to get an idea how large is that unit. Yeah, so in certain number of nanoseconds. In our modern computers, yeah, PC, here I'm talking about PC, not supercomputer, PC, in certain number of nanoseconds, yeah, actually 1 or 2, yeah, that's small number, okay, 1 or 2, yeah, that's small number, yeah. Yeah. Could be faster than that if your computer is better, yeah. Yeah, more expensive, it could be faster than that. Yeah, but here you can imagine just 1 or 2 nanoseconds. How large is a nanosecond? Yeah, here, we know 1 nanosecond equals 10 to the negative 9th second. 1 billionth, yeah, this number, 1 billionth of a second. That fast, yeah, that really fast, okay? Yeah. All right, analysis. It is allowed to add reasonable assumptions. So here we add assumptions, but some people may ask why you can do things like that. Yeah. Here, the reason is simple. Yeah. The added assumption should not alter the original problem significantly. Now, here, even after we add assumption like this, still our problem has the same difficulty as the original one, right? Yeah. We do not make the problem easier, right? Yeah. Yeah. We just, provide some convenience in our analysis. Yeah. We do not make the problem easier, significantly. It changed the difficulty level significantly. Yeah. Okay, yeah. So we solve the same problem here. Okay, yeah. It simplifies the setting without changing the difficulty. Okay, yeah. All right.